310 is this idea that we can use differentials. What are they good for? Well, they're good for approximations and estimations. So one case in particular is you can do error estimates using differentials. So differentials are useful in approximating or estimating maximum error. You'll have some problems like this at the end of your homework assignment. Here's the really general idea. If you're given a function y equal f of x, and you're given a possible error for the input values, okay, then the actual maximum error in the outputs is approximately given by the differential, okay, of the dependent variable. So the differential here. So this is what we would call the estimated maximum error. So it's an estimate though, and it's much easier to compute in general than the actual maximum error. Okay, so that's why we're going to use this estimate of the differential, because this just comes from, it's using a line basically to estimate your error. And then we know from the previous example that the differential is just f prime of x times dx, the dx differential. As a side thing, here the relative error is equal to the actual error over whatever function value we were interested in. And this is, again, estimated by taking the differential and dividing it by the function value. The percentage error, all we do is we multiply the relative error by 100% just to turn it into a percent. So the estimate that we're going to use is we're going to take the estimated relative error and multiply by 100%. I'm going to do an example just to make this a little more clear, but these are the three things you want to remember for your homework. Now, let's take a look at this example. Okay. So the edge of a square was found to be 10 centimeters with a possible error in measurement of 0.6 centimeters. So what this is saying is you've got this little square, and it's about 10 centimeters in length and width, but it's possible that there was an error in measurement of 0.6 centimeters. So in other words, maybe the square is actually a little bit smaller. So maybe it could be as bad as 9.4 centimeters, or it could be as large as 10.6 centimeters. Okay, so this is just the maximum possible error in the measurement of the input. The square could be a little bigger or a little smaller. So the idea is that we want to know what is the range and the possible errors of the area, okay, based on the errors in the edge length of the square. So how much could the area actually vary because of this error? So I'm going to let x represent the length of an edge, okay? And so here x could be off by plus or minus 0.6. And let's continue reading. Use differentials to estimate the maximum possible error, relative error, and percentage error. So these are all estimates in computing the area. So I'm going to use a for area as a very just natural variable of the square. Okay, so the first thing I'm going to note is that the function, so what would correspond to y in these formulas, the function here is just, I'm going to call it a, and it's just the area function is what I'm interested. So area is a function of the edge length, and it's just equal to x squared. Now the derivative of the area function is just 2x. So my area differential is given by dA equal to, now I'm going to take a prime of x times dx. So the differential is 2x times dx. So that's my differential. Now remember that the differential gives us the estimated maximum error. It's just an estimate though. So let's see. So here I have the my differential dA. Now in this case, x would correspond to 10. Okay, so when the square is 10 centimeters in edge length, and the possible input error is dx, so that's going to be 0.6, then I get that the differential dA is 12. So what this is saying is that the estimated maximum possible error in the area is 12 centimeters squared. So this is the estimated max error when edge is 10 centimeters and possible edge error is 0.6 centimeters. So this is the maximum that the area could vary. So that answers the first question. Using that, we're going to say that the relative error, and again, this is an estimate, is equal to dy over y. So this is just going to be 12. Or let's say in this case, I'm going to name this dA over a because I'm using a for my function. So this is going to be 12 over, now a is equal to a of 10, which is 10 squared or 100. It's just the area if there was no error. So this is over 100, which gives us 0.12. So that's our relative error estimate. Finally, we have the percentage error. And all we do is take the relative error estimate and multiply by 100. So that's just 12%. Okay, so there you have it. This is the estimated max error. This is the relative error, and this is the percentage error. These are all estimates.